I'm Seunghyun, and I'm a committer and PPMC of Apache Pinot project, and I have worked in Pinot team at LinkedIn for about 3.5 years. And today, I'm going to talk about our journey to scale Pinot for member-affecting use cases. So let's get started. So at LinkedIn, impression discounting technique is widely used for improving relevance score for recommendation engines. So the high-level idea is not to recommend the same items over and over again if the user has already seen this item for multiple times. So in order to achieve this functionality, we are applying a discounting factor computed as a function of item impression count to the ranking score in real-time fashion. And impression discounting also prevents the recommended items from being stale. So for example, if you refresh the LinkedIn main feed, then you'll see that the recommended items will continuously change. So if the Pinot is somehow down for some use case, then the main feed will actually become stale. And impression discounting is used by more than 10 plus relevance use cases, including feed items, jobs, potential connections, and ads recommendations. So let's first take a look at the architecture of the impression discounting use case. So let's say that we logged into the LinkedIn and we watched some posts recommended by the feed. Then under the hood, these activities will be tracked. So events indicating member X viewed item I1 would be generated to a stream source like Kafka. Then the data from the raw tracking topic will be consumed by the Samza, which is the stream processing engine. And by the way, Samza is also developed from the LinkedIn, and it's an open source project. And in Samza, we extracts and transforms the events and writes to another Kafka topic. And that topic will be again consumed by the Pinot. And both raw and processed data are written to the data lake, and they are used for the offline ingestion to Pinot. So while the data is ingested to Pinot, the application servers are continuously querying to Pinot, and it will ask Pinot that how many times member X has seen items I1, I2, I3, and so on. And then the Pinot will compute the query on the fly and give the counting results back to the application servers. And then by the time that we reload the feed, for this particular example, item 1 will not be shown at the top because the impression count is already updated in real-time fashion in Pinot. So out of all the impression discounting use cases, we initially decided to tackle the feed impression counting use case because it was by far the largest use case. So we thought that if we were able to successfully onboard this one, all other impression discounting use cases can be easily onboarded. So let's look at the this feed impression counting use case specifics. So the schema is pretty simple. The table has the member ID, item, action, timestamp, and count columns. And the query pattern is pretty much fixed, but each production query would fill the different member ID and item values. And as you see on the SQL query on the screen, the query basically computes the impression counts for items over the sliding window time. And it also has some extra filters. For initial SLA requirements, we had to support the high query volume, as high as 3K QPS at the peak. And we had to support to serve this use case within 100 milliseconds for 99 percentile latency. And we also needed to support to ingest at 100K messages per sec, along with hundreds of billions records for the entire table. So when we initially got this use case, we looked at the schema and the query pattern, and we tried to apply all the optimizations available at the time. So one thing that was stood out was the fact that we always have the equality filter on the member ID. So we applied the sorted index for the member ID column because the sorted index performs much better than the inverted index. And for item, action, time columns, we compared the performance with and without the inverted index. So for this particular use case, scanning was actually faster than using an inverted index because the number of rows after the member ID filter was not too large. So scanning cost was actually cheaper than the large bitmap operations by the inverted index. Moreover, we pre-aggregated data based on the days since epoch timestamp to reduce the data size. And for real-time server, we used the low-level consumer instead of high-level because high-level consumer had a scalability issue because a single server consumes from all partitions, and this use case, the ingestion rate was way too high. So using low-level consumer solves the scalability issue by allowing its server to consume from a subset of partitions. And after we applied this low-level consumers, we were able to consume the events without any performance issue. So with all these optimizations applied, our initial baseline performance was still not so good. We were actually able to serve about 50 QPS within SLA from a single machine with partial data loaded. Then we also set up the cluster of 25 nodes, 15 offline and 10 real-time servers. And each server was loaded with 16 cores, 64 gigabytes RAM, and each of them were attached with the SSD disk. So when we ran the queries at 3K QPS, we were not able to scale. And this was kind of expected based on the single node performance. So we asked ourselves, can we do better? And actually, this was the start of our journey to scale Pinot to the next level. So before we start to talk about our journey, I think it's important that everyone to be in sync on how Pinot processes the query at the high level. So first, the Pinot broker gets the queries from the users, and broker routes the queries to both real-time and offline servers, and it collects the results back from servers. Then the broker combines the results, and it returns the final results back to the users. So in order to improve the query performance and scalability of the Pinot, we had to look into the individual components such as brokers, real-time servers, and offline servers. And we also had to look at the holistic picture as well. So in the first stage, we first focused on optimizing single server level query performance. So we first identified the bottleneck on the data storage format. Pinot segment is the basic data unit for Pinot table. And the segment is composed of the forward index, metadata, and other special indexes such as inverted index and starter index. And by default, Pinot generates a dictionary for forward index to look up the data when given a document ID. So in general, dictionary is a great way to compress data, but the cost is to have an extra random IO lookup when accessing the actual column value. So for this particular use case, the item column actually had an issue with the dictionary. We found that the 70% size was wasted due to padding because of a few long item string values. And by the way, we used the padding to make the dictionary value to be fixed size because we can easily use binary search when the value size is fixed. And also, the item column is a high cardinality column, so we didn't actually get the good compression rate with the dictionary encoding. So we actually did not get any benefit from the dictionary while we were paying all the cost of the dictionary. So the solution was to implement the raw forward index without the dictionary. So the idea is pretty simple. So we store the raw column values in a chunk, and the chunk is composed of header and payload. So we store chunk offsets in the header, and we store the actual column values in the payload. And when we need to access the value given a document ID, then we can look up the offset from the header, and then we read the actual values from the payload with the offset information that we got from the header. So the raw forward index directly eliminated all the padding issues, and it reduced the item column size by 7%. And moreover, we were also able to get a benefit from the sequential IO. Because the data was sorted on member ID, all the item values that we needed to scan were actually stored together in a chunk. And on the other hand, one disadvantage of this raw forward index is that the data size can be large if the cardinality is small, because we store the repeated values. For this case, we can optionally compress the chunk using the snappy. And another bottleneck was the fact that we always process all segments for every single query. So we realized that if the data is partitioned on the member ID, then we can skip a lot of segments from processing. So to support this, we implemented the feature that supports custom partitioning on arbitrarily dimension columns. And we also implemented the segment pruning mechanisms based on the partition information. And this feature actually reduced the number of segments being processed from 1,000 segments to 30 segments per query. So after applying raw forward index and data partitioning features, we were able to get some numbers for 3K QPS. And we were actually able to process 3K QPS at about 270 milliseconds for 99 percentile latency. So by this point, we thought that the storage format and query execution path was pretty well optimized. So we turned our attention to the broker, which deals with the query routing. The main bottleneck for broker routing was from the fact that we query to all servers for each query. And if we do so, adding more servers doesn't scale after a certain point because 99 percentile latency is dominated by the slow servers. And the solution for this is to control the number of servers to fan out. So we introduced the concept of replica group, which refers to a set of servers that serves a complete set of segments for a table. And we also implemented the replica group aware segment assignment and routing strategy. With those, we were able to route the query to a single replica group instead of all servers. And we still get the correct answer because servers from a replica group are guaranteed to serve all segments for a table by definition. Given that we query to a single replica group per query, we now can add more replica groups to increase the QPS capacity. So this feature provides the true horizontal scalability to Pinot. So after we applied the replica group segment assignment and routing, we were able to cut extra 50 milliseconds for 99 percentile latency using the same 25 nodes. And I would like to re-emphasize that with replica group segment assignment and routing, we can now support even larger QPS than 3K. We can simply add more replica groups to increase the capacity. So at this point, we were kind of out of the ideas about what the potential bottlenecks can be. So we decided to go over iterations of performance profiling to find the hotspots and optimize the code for each component of the Pinot. So while profiling Pinot components, we actually identified some inefficient codes, and we also optimized a lot of them. So one example is the top-end computing algorithm on the broker side. Originally, the code was naively adding all elements to the heap and popping n elements for the computing top end. And this algorithm uses a lot of memory and also wastes a lot of CPU cycles to rebalance the heap and heap data structure. So the better algorithm would be to push until the heap size becomes n and push only if x is larger than the mean value of the q. And another interesting fact that we found was that the string operations were very expensive. So we removed all the unnecessary JSON serialization and deserialization processes. And we also removed unnecessary string conversions, such as string.format, string.split, and string.join. So surprisingly, this profiling and fixing hotspots provided us the great performance boost. We were able to cut about 120 milliseconds for 99 percentile latency. And we were, at this point, we were very close to satisfy the SLA. After we cleaned up our code a lot through the performance profiling, we found that the real-time servers are now having the higher 99 percentile latency compared to the offline servers. So the main difference between real-time and offline server is that the real-time server ingests data from the streaming source. So we closely looked at how real-time ingestion affects to the query performance. So Pinot has been using off-heap technique for loading immutable segments to avoid the data get managed by the garbage collector. We support both mmap and direct byte buffer for this. However, for consuming segments on a real-time server, we used to store consumed data on JVM heap. And this actually adds the pressure on JVM, and it triggers very frequent garbage collections. So in order to reduce the GC on the real-time server, we implemented the off-heap consumption feature, which stores consumed data to the memory space that is not managed by the garbage collector. So usually the downside of this off-heap technique is that the performance is slower than the JVM heap. However, it turned out that even our initial implementation performed pretty well at the ingestion rate of 100K messages per sec. And in today, actually, this off-heap consumption setting is applied by default for all use cases at LinkedIn. Another issue that we found from the real-time server was the large-sized segments. So while the data is pre-aggregated based on days since epoch for offline servers, we used to append one row per Kafka event. And this actually makes the real-time segment contain too many rows for use cases with very high message throughput. So to fix this, we implemented the aggregate metrics feature that aggregates data on the fly for consuming segments. And one direct benefit is that the real-time segments becomes much smaller, and this feature improves the query performance by greatly reducing the number of documents that needs to be scanned per query. So with the off-heap consumption, we reduced the GC on real-time servers, and aggregate metrics improved the query performance by reducing the number of records for the real-time data. So after applying those, we were able to cut extra 20 milliseconds, and we finally achieved the SLA for the feed use case. So our journey actually started from the point where we were not able to run 3K QPS at all. And we finally achieved the 80 milliseconds for 99 percentile latency at 3K QPS. And this was actually a very big win to us. So after solving this feed impression counting problem, which was by far the largest use case for Pinot, we started to onboard all other impression discounting use cases that we had using the similar configurations that we used for the feed one. So in today, we have more than 10 plus impression discounting use cases that we support at LinkedIn. And we process about 50K plus queries per second for all the impression discounting use cases. And this is actually a huge number because this is about 50% of entire traffic of the Pinot. And we also process all those queries within 100 milliseconds for 99 percentile latency. So I would like to close the talk with the takeaways. So traditionally, key value store is widely used for high throughput, low latency use cases, while the columnar store is used for complex analytics queries with low query volume. So the supporting impression discounting use case was a challenge, but it pushed the limit of Pinot to the next level. And we also proved that the high throughput, low latency use case can be actually served by the columnar store. And the second point is that the profiling is very important. As seen in the previous slides, the small code change can actually make a huge performance improvements. And lastly, working on Pinot is very fun. While working on impression discounting use cases, we were exposed to all different aspects of the systems. We dealt with the low-level systems such as data storage format, query execution engine, and garbage collections. And we also were exposed to a lot of distributed system concepts, such as segments assignment and routing, partitioning, and replication. So if you're interested in systems, in my opinion, Pinot is a really great project to work on. And we are open source, and we are looking forward to see more and more contributions from the outside. So if you have any questions, please add your questions on the website shown on the screen. And this is all I prepared for today. Thank you.